Alright, doing a response video to this Michel van Biezen guy. Professor, somewhere in California, I think. Anyway, so he does these lecture on ilectureonline is his website, and yeah, I like these videos. And so I thought I would respond to it just because I don't like the way he's doing this description of light diffraction. And so he has a number of videos on single slit and double slit and triple slit, and it's all got some great math in it and all that kind of stuff, so it's really good stuff. But conceptually, I don't think it's right. Yeah, I think the math is right, but I don't think the causes are accurately being described. What's creating the wave function in photons? Yeah, so we'll just play this and I'll respond. I have a couple of questions. I guess I might as well get to a couple of the questions. Just curiosity questions. I'm curious what the diameter of an electron is, or its orbit. I just don't know. It'd be interesting to know because of my theory. And also the atoms jiggle. Now, whether the nucleus jiggles or not, who knows? Jiggling is the word Feynman used, so I'll use that word. They vibrate. I was wondering what the displacement is of that vibration. What's the total displacement of the average atomic jiggle? Be interesting to know that also. Because I guess I'm sort of arguing that its jiggle is not of one speed. It doesn't just go one speed and get to this side, go the same speed back. Now it actually jiggles, like all wave functions are created, by moving faster than the wave function. So it accelerates to the midpoint, decelerates to the end point, then has to re-accelerate to the midpoint, deaccelerate again to the maximum. So it's spending more time in different locations in its jiggle, and that is what's creating the wave function described in quantum mechanics. It's electrons moving through their cycle of jiggling that's creating the probability, because there's a probability of what part of the cycle an electron will be in. A higher probability at the outermost points because it's moving slower, because it has to decelerate and reaccelerate, and a lesser probability in the midpoint, and less time in the midpoint, and more time again at the other end. And it is that pattern that is reflected in the on-off diminishing interference pattern. It's not a wave interference, it's a cycle interference, the cycling of an electron. So that's my contention as an explanation for the effect. Get up on your chair there, buddy. Okay. Hope he didn't pee on anything.
Hey, welcome to ilectureonline. In the previous few dozen videos, we talked a lot about diffraction. We did not. No.
He's going to start over now. Okay, so he has an outtake. Should be on the outtake video.
Welcome to ilectureonline. In the previous several dozen videos, we talked a lot about interference patterns between rays going to multiple slits, 2 slits, 3 slits, 4 slits, and so forth, and we had all kinds of what we call interference patterns. But the one thing that we ignored to mention was that anytime light goes through a very narrow slit, there's also diffraction. And what happens is...
Okay, so yeah, on the subject of diffraction, so he has this, these lines pointing in a direction. So, this assumption that there's a wave coming in, okay, I'm saying it's not a wave coming in. What's happening is these two slits, or the two sides of the slits, are vibrating. And as they vibrate, like I said, they're in the maximum position more time than they're in a minimum position. And they might be vibrating out of cycle, depending on the thickness, the density of the material. But regardless of the cycle change, they're probably synchronized to some extent, because you would assume there's some communication with them electrostatically. And so my argument would be is anytime you come anywhere close to a material object, there is not a fine line here, like this is matter and this is not matter. all matter is surrounded by a field and a density of electrons. And so there's a density of electrons on the two sides of this slit. And those electrons are certainly capable of diffracting or bending light. And that's what's causing the diffraction pattern, is the fact that the slit is narrow enough to maximize these fields of electrons, and those electrons are denser as you get closer to the slit, and that density, the probability of hitting one of those electrons, is what's creating the diffractions. And the electron's vibration is what's creating the manifestation of pattern. But anyway, this straight lining thing, this middle one would never go at an angle. There would be no diffraction in the middle. So I don't really like the way he drew this. And I'm not saying he's arguing that this middle photon would do this. But again, part of what he's going to argue here is that these light beams are interfering with each other. And so my first critique of this, the first question I would ask is, has the single slit experiment that you're describing here, that has some diffraction pattern, I mean, it's washed out basically because most of the light goes through the center, and so you barely see these lesser humps. You're saying it's 1/3 the intensity. Well, that doesn't show up when people do this experiment. The first argument I would make is you're showing a diffraction pattern that probably isn't visible, because every time they describe the 2-slit experiment, they always show the 1-slit version, and they see it's just a blob. See, there's no interference when there's 1 slit. They're always saying no interference. So you're arguing that there is interference. You're saying that diffraction is essentially canceling out interference. You're saying it's wave function interference is how diffraction is manifested, and because it's bending the light and forcing the light to combine. And so I guess the first question would be, if I sent single photons through this experiment, randomized them so the same exact pattern, just did a single photon at a time, would I get the same pattern? And my argument would be, then how do you explain the photon interfering with itself when there's not 2 slits to go through and it doesn't create 2 waves? If there's only 1 wave, how is there any diffraction? And I guess I would argue, is there any evidence that if you send single photons, you get a different pattern? Because if you get the same pattern, you can't argue it's canceling out. The other thing I would say, canceling out is always a problem for me. So when you say the 2 waves are out of phase, exactly 50% out of phase, and so they cancel each other out. No, they would cancel each other out when they were exactly in phase. Just one complete phase shift out of phase. Something like that. Anyway, the argument is they're canceling each other out as a wave function. How can they do that? Photons don't cancel each other out. So you're saying they cancel, somehow they say no to a location and somehow go somewhere else. So you talk about them as if they're a beam, a photon, and they're both going somewhere, and they cancel each other out. Well, they can't cancel each other out. So you should at least say that you believe in the Copenhagen interpretation or something. You have to have some interpretation to go behind that statement, because how else is this wave function or this canceling out taking place and the photon not being destroyed? I mean, light is rays of light. It doesn't move as a wave. It moves as rays of light, maybe traveling on a wave, but you just can't have it both ways. So where does it go? So when it doesn't go here, what line puts it over here instead? What mechanics? I mean, you're drawing mechanics here. What mechanics takes it from this and says, nope, can't go here, we have to go over here? How does it do that? Not that you have to answer the question, I'm just saying you can't really draw a mechanical drawing and then just say, well, yeah, it doesn't really cancel out. It just cancels out its wave portion, but the photon actually lands here, and have no way to draw that backwards, because there's no way the light can do that. There's no way you can get there from there. Okay, that's what I'm saying. All right, and what else do I want to say? Yeah, one photon at a time. So that's the important two questions I had, besides the other two previous ones. So I didn't want to get to all the questions at this portion of the video, but I did, so good.
We just simply take a single slit right here. The width of the slit is equal to A, and as light goes through the slit, and if the wavelengths of the light are similar in size to the width of the slit, then the waves, the energy of the waves will diffract or bend around the opening of the slit.
Okay, so again, he's really, the energy of the waves. He's obviously completely committed to this idea that light is a wave and that it isn't a photon, it isn't a thing. So I just for clarity, I mean, I'm arguing that everything's photons, and that any light that you see is more than one photon. Technically, it's two photons separated by a distance. So the two photons have to maintain their integrity, have to follow each other through whatever system they go through. But that's not as important a point. But it might explain why prisms separate light and all that other kind of stuff, is that the photons are actually changed. But anyway, I won't even get into that one. But that's important to diffraction, which is exactly causing it. So, yeah, this diagram isn't really, I don't care for this one.
Go in all different directions. And what happens then is that the different portions of the beams will begin to interfere with one another, just like when we have multiple slits and the light coming through multiple slits interferes with one another.
Okay, but again, when they do the two slit or multiple slit experiment, when they close all the other slits and just leave one open, the argument is that there is no pattern. They keep making that argument. There's no pattern. There's no pattern. So they can't have it both ways, right? And again, you're saying there's an interference pattern created by a single slit. So what I'm arguing is, if I send single photons, you won't be able to say the photon went on this edge and it went on, another photon went on this edge. You'll only have the one photon and you only have one wave, and there won't be any way to, you get me?
Same will happen with different portions of the very same beam going through a single slit. There will be an interference pattern, and because of that, we have an overall diffraction pattern. So the bending of the light is called the diffraction, and because of that, there will be mutual interference between different portions of the beam going through a certain part of the screen over here, and because of that, we'll have high and low intensity regions. High intensity, low, high, low, high, low.
Right. So again, just for clarity, the argument I'm making is that the light is dead. Light doesn't have any wave function. It doesn't have anything. And the only time it acts as if it has something is when it interferes with matter, an electron. Okay, something, it has to interfere with something bigger than itself. That light doesn't interact with light. You can't make two photons interfere with each other. You can't make them do something with each other. They just won't do it. And that the only thing you're doing is changing the direction of the light by having the light interact with electrons, which are vibrating. And depending on the cycle of the vibration will dictate where this light beam will go. So depending on at what point in the cycle of vibration is going to dictate where this pattern is going to show up. And as I'm arguing, as the speed of that vibration changes with time, so it's going faster, I mean it spends more time out than in, and that is what's creating these patterns, is that there are certain patterns to the vibration. The vibration has a pattern, and that pattern is what is creating this pattern.
Notice that the diffraction pattern kind of decreases in intensity. The maxima, as you go further and further out away from the central maximum, becomes smaller and smaller and smaller, meaning the intensity becomes smaller and smaller and smaller as you go further out. Right,
so I guess I'd just say it's a superficial thing that causes some confusion here. Remember, he's describing a single slit here, and he's describing a pattern that you usually don't see unless you do this very carefully. So, I mean, from my personal experience anyway, it's not that easy to create this phenomenon in light. And what I would also argue is that if you look at this pattern, it is also the same pattern that would be described as Newton's rings. So anytime you put light through an aperture, you create these rings. Well, that's because it's a round aperture, and so you end up with a ring. But that's exactly the same kind of pattern. Those rings are doing the same thing. There's a higher density of light in one location, a less density of light in another location. It's the same pattern. So again, just for clarity, the argument made in the two-slit experiment is that the single slit doesn't have any of these patterns, that it doesn't have any phenomenon. And now you're saying it does have a phenomenon. And that's a little bit confusing. And you're saying, I mean, you have it rather dramatically portrayed here, and that's not what you're going to see if you actually do this experiment, unless you do it very carefully.
What we will see later is that when we combine the diffraction properties of light with the interference properties of light with multiple slits, that we have to take that into account, and that the intensity...
Yeah, well, see, the problem I'm having with what you're saying is that you're saying the diffraction pattern is already an interference pattern. You're saying these beams cancel each other out. So you're talking about an interference pattern. So you've changed diffraction into an interference phenomenon rather than a phenomenon of light being bent and the photons doing what light does, going in straight lines. So I don't think it's a good combination.
The intensity of the interference peaks will diminish because of the diffraction pattern that will then be overlaid with the interference pattern. We'll see that later. What we have to understand here is, if you kind of take a look, notice that if we take a specific spot on the screen right there, and we see that different portions of the beam travel towards that spot, that the portions of the beam that are down to the bottom have to travel a greater distance than the portions of the beam at the top. For example...
Okay, so I guess another point I want to stress again, what I would argue is what's really happening is that the light coming through the center here has very little diffraction. The light coming to these edges has more. So the closer you are to this edge, the more likely you are to diffract to this furthest point. And the further you are from this edge, the less likely you are to, and that is what's creating the diminishing cycle, is that there's just less likelihood of light being in one of these specific locations. The density of light in the center is greater, and the likelihood of interaction is only intense in this small areas doing the hardest diffraction. There's more diffraction the closer you are, so I guess that's the argument I'm making. There's more diffraction the closer to the surface, and there's less light proportionally that'll be close to the surface. So that's why there's less here, is because there's less light that's doing the most diffracted. Most of the light is being minimally diffracted, where only the portion that goes right near the edge here is being diffracted.
If the ray at the center of the beam has to travel exactly a half a wavelength farther than the very beginning of the beam, then this ray and this ray will cancel each other out, and there will be destructive interference over there. And if you then take the next beam...
So again, that word, this ray will cancel each other out, right? Well, that isn't happening. The rays are not canceling each other out. So let's just be clear on that. You can't do that. You can't destroy the photons. So the photon went somewhere. You can say it canceled out this location as a possibility and chose some other location. But again, you're not going to explain to me how it chose that location.
Over there and the next beam over here, those two will cancel each other out. And if you take the next beam and the next beam, those will cancel each other out, because you'll have pairs of portions of the beam that are simply a half a wavelength out of phase, and so when they get to the screen, half a wavelength out of phase means destructing the fixture.
Okay, so let me just be clear. So you're saying that if I sent single photons through here, that wouldn't happen. There would be no pattern, because there would be no way for a single photon to go through two portions of the slit and create any kind of divergence in its destiny.
interference, and you will not see anything, and you actually will get a minimum right there to exist. In other words, half the beam will cancel out the other half of the beam, and the result is you'll see no light there at all. There will be a minimum. So that's the concept of what we call diffraction. And
yeah, sorry, I am using a wide-angle lens, so I am diffracting you pretty substantially, but yeah, it's not too bad. So anyway, continue. No real complaints except for this idea of using the word beam when you're describing waves, and you know, I just don't think, again, let's just be clear, I don't think light has any wave function. It only appears as a wave function when it interacts with vibrating electrons. Vibrating electrons create the appearance of a wave function because vibrating electrons create the wave.
Diffraction will cause diffraction patterns on the screen, which will have to be taken into account when we look at not only single slit situations, but also multiple slit situations, and we'll see that in some later videos. Again, what we can see here is that the extra distance of this portion of the beam, halfway through the slit, so if we go from there to there, that's the width of the slit, and this is halfway through the width, so we can see that this extra distance traveled by this portion of the beam compared to this portion of the beam is half the width of the slit times sine of theta. And if those happen to be exactly half wavelength out of phase, so if this is equal, I'll put an if on there, if this is equal to a half a wavelength, then those two will destructively interfere with each other, and therefore you see a minimum over there. So that's the basic concept. I don't
well, again, destructively interfere with, but in a way that is nothing to do with where the actual photon is going, except for the fact that this is some sort of, it's saying don't go there. It had to go somewhere else, and again, there's just no explanation of where else it's going.
Now, I don't expect that you understand exactly the whole thing about diffraction, but at least the basics of diffraction, that if you have a single slit, different portions of the beam will interact with each other.
Okay, different portions of the beam. So again, if we send single photons, there won't be any different portions of the beam.
Will be either constructive or destructive interference, and therefore you'll see either a minimum or a partial maximum. A partial maximum means that not all of the beam will cancel out with the rest of the beam, but that a small portion will actually get through, and therefore you see a maximum, a diminished maximum in a way, away from the central maximum.
So again, I would argue that it's just a reflection of the fact that the maximum amount of diffraction is happening very close to the edge of the slits, and only 1/3 or 1/6 of the photons are flying through that dense area of electrons.
All right, hopefully that gives you a kind of a feel of what this is about. If you're interested in diffraction, keep watching. I'll have lots more videos that tell you exactly how to calculate all the various things about a diffraction pattern. And then later we're going to combine that with interference patterns to see how that works with multiple slits. Because
so I made this before I'd seen the other double slit videos. So there is a lot of it, but a lot of the math is redundant, and I'm not saying the math isn't valuable, but yeah, I just want to make sure the cat's not up to anything. The point I would argue is that these variables are the important thing that we're manipulating. And for both theories, the variables are the same. The width of the slit's important. Instead of the wavelength of the light being significant here, I would argue that it's the vibration of the slit material. So we could just replace those two variables, and you're saying the light's creating the function, I'm saying the electrons are creating the function of the initial wave, or the initial the carrier wave. The carrier wave is being created by these things vibrating, not these things vibrating. Okay, so on to number 2.
Welcome to ilectureonline. Continuing with some of the basics about diffraction, we're going to try and understand really what causes diffraction in the first place. Well, diffraction is really the principle of light going through a narrow opening. If the wavelengths of the light are at par, about the same size as the opening itself, then the light will what we call diffract around the corners and go in every direction on the other side of that slit, on the other side of that small narrow opening.
Okay, so let's understand that a single photon isn't going to do that. It's not going to go every direction. So again, we're talking about some sort of carrier wave, and the photon is going to end up where some sort of probability is going to dictate. So again, you're back to some sort of Copenhagen interpretation, I would imagine, that is founding this. So, you know, I don't know, you know, I'm just saying, I don't, you know, it's just, there's no, I guess in a point to a point, there's no point in drawing drawings because the drawing doesn't reflect what light actually is. But anyway, I guess I'd also, just for clarity, I guess he could have pointed out that this diffraction is likely to be in this direction. I mean, it's more likely to curve around a surface than it is to be scattered that way off the surface. And, which I think is important. And again, that it's more likely the photons that are in the portion of the slit that's closest to the edge of the slit are the photons that are going to have the most dramatic diffraction. I think that's two. I think those are truths.
Let's say the distance of the opening is A, so that's the width of the slit, and so we can then imagine that light will go in all different directions. But instead of seeing a pattern over here where you have a bright spot here and then it slowly diminishes in strength as it goes out, we see a very interesting what we call diffraction pattern, where we see a very strong central maximum, then it goes down to minimum and to zero, then we see a secondary maximum, a third maximum, and so forth.
So again, he's saying it goes down to zero, and I don't think that's true. Zero. And I don't only think it's true. See, there's another component to this, and I think it has to do with how much light there is. So, like many other circumstances where light interacts with substances, it can use up the catalyst for diffraction. So in a sense, you could use up the diffractable electrons if you flood it with enough light. And so that this pattern would be completely obscured by the photons that didn't interact because the electrons were already busy interacting, let's say. They were already being consumed as refracting electrons. They can't refract two photons at the same time, or some rule like that. Yeah, so again, you're talking about special conditions, because this clearly is not the argument being made by quantum theorists about the two-slit experiment. They constantly point out, again, that there is no pattern with one slit. So, you know, I'm just saying that that's clearly what they say. So you can't say there is a pattern when they say there isn't a pattern without some explanation.
And as you go further out, the size or the intensity of those adjacent maxima decreases as you go further and further out. And in between, you have those areas where there's a minimum. So what causes that? What is the reason why we have that interesting pattern? And also there's some associated equations that we're going to develop, and they're going to come over here. We're going to develop some equations where we can easily calculate what that diffraction pattern looks like and what the intensity of that diffraction pattern looks like at different places along the screen on the other side. What we have to realize here is when we have light coming through a slit, realizing it's going to diffract everywhere, what happens on the other side when the light actually hits the screen? Well,
so again, I guess I would argue that you kind of have to argue that light is photons, and so you have to kind of say when photons do this and when photons do that, you know, because just to say, okay, light goes through the slit and interferes with itself again. We're back to this interfering with itself thing, and it's just,
imagine for a moment, you look at the screen directly across from the opening. All the rays of that beam will have to travel the exact same distance, and so since all the rays travel the exact same distance, there's no what we call interference at all, because they all come in at the same phase, and so you see a very strong central maximum right here. But as you then look a little bit further up, then you realize the portion of the light that goes in this direction, notice that at the top of the beam, those rays have to travel a shorter distance than the rays at the bottom of the beam. And you can see that.
Okay, see, so top and bottom of the beam is almost implying that the photon hits both of these edges and then diffracted to a point and then said, no, we can't go there, we have to go to the maximum. So I guess he's arguing that this would be here's the central maximum, this is the 1/3 intensity, minor maximum, and this would be 1/6 the intensity, I suppose. But again, I would argue that that's only a reflection of that you have the highest diffraction closest to the surface of the material.
At the bottom beam, this would be the exit distance traveled by the rays at the bottom of the beam compared to the rays at the top of the beam. If we then again look at the rays that go a little bit further up in this direction.
So again, he's saying the word rays, okay? And the rays are not, there's not more than one ray here. In strictly speaking, again, we should be able to use the same diagram for single photons at a time as for a beam of light. So if this was a single photon at a time, you can't really argue that it has a ray that goes in 2 places or 10 places or all of that.
Notice that extra distance traveled by the bottom of the beam becomes larger and larger and larger as we look further and further up the screen this direction. Of course, the same will happen in the other direction right here.
Right, and so let's also understand that what's going to dictate how much diffraction there is as you narrow this slit, you increase the percentage, you decrease the percentage of light that has a chance to go through unmolested. So if we perceive this slit material as being active with electrons around it, and we say that those 2 fields of electrons might have a perfect distance where the 2 fields just hit each other in the middle, so that every photon would be slightly diffracted depending on how close they were to that field. So just like gravity, the field would get stronger, the closer you get to the actual surface. So the gravity is the strongest right at the surface, and that's where you have the maximum diffraction. So it's a lot like Einstein's lensing even. It's right at the surface that you have the highest diffraction, because that's where there's the highest density of free electrons. Associated electrons. They're not free, but they're associated with the material of the slit. So again, one of my fundamental arguments in all of this quantum mechanic description is the fact that in none of these descriptions, in none of these interpretations, is anyone ever accounting for the fact that matter and non-matter don't have a barrier that is some sort of perfect barrier. The barrier is a bunch of electrons vibrating. It's not just, you just don't go from a slick surface that says this is matter on this side and it's non-matter on this side. Matter has a zone of permeability, a zone where at any one moment there could be matter there, and at any one moment there could be no matter there. It has a, well, I mean, field is a good word, but field is a little, I don't like that. That word's been ruined too. But it has an area of diverse substance, inconsistent substance. Is that a good way to say it? A zone of inconsistent substance.
The key with understanding a diffraction pattern, because we're not dealing with 2 separate beams like we do in a double slit interference pattern, here we have...
Yeah, I know, but you're saying it just like we are. You've said it more than once. Come on.
It's a single slit, and the key to understanding a diffraction pattern is to realize that as you go further and further in the beam, the rays, the adjacent rays in that beam will travel farther and farther distance. What we look...
Okay, so again, the rays of that beam. So it's again this idea that the beam doesn't just come in and go one place, it's going all these places, and then it's deciding somewhere in all of that stuff that, no, all of these places are no good, I'm going to go over here. And where my interpretation would be that no, this is vibrating, the photons travel in straight lines, they go from point A to point B. The point A, the refraction with the electron has been different because the electron's in a different phase of its cycle, and in the different phase of the electron cycle, if the photon meets the electron and the electron's in the outward phase of its cycle, it'll get diffracted a lot, and if it's in the inward phase of its, the middle phase of its cycle, it'll get no diffraction. That would be the argument, is that those two places have completely different diffraction potential. So there's high diffraction when the electron's eccentrically or farthest away from, say, the nucleus of the atom, and there's no diffraction when the electron's in the position of its orbit where the nucleus is in the center of its orbit. Something like that. That would be the explanation for why there's a probability of certain levels of diffraction. But each photon actually diffracts. Each photon just goes straight lines. It doesn't. The photons do not interfere with each other. The interference is there is no interference. The interference is a byproduct of the vibration of the electrons. The pattern is a reflection. Remember, the pattern is just a simple pattern. 10, 7, 3. It's that kind of pattern. It's a consistent pattern, and consistent patterns can be created by a lot of things besides wave interference.
4 is to point at the beam where the extra distance traveled by a ray in the beam is exactly half a wavelength farther than at the very beginning of the beam. Now, if you just look up at a shallow angle like this, if theta, and this is the angle theta, the lookup angle, theta, if theta is small, you can see then you have to go quite a ways into the beam before you find the spot in the beam where the extra distance traveled is exactly half a wavelength. If you look further up, if theta is a larger angle...
Okay, so again, I would argue that this never happens. Okay, that the photons never diffract this much from the center position. Center photons go to the center of the target, and it's only photons have to be in this higher density area to do this greater diffraction.
Then you don't have to go as far into the beam to find the point where the extra distance traveled is a half a wavelength. Now, the key again is that if you imagine that there's a wave going along here at the very top of the beam, and then there's a wave over here, and this second wave travels exactly...
Again, so he's describing two waves, which is essentially describing two photons, which again isn't supposed to be a phenomenon created by single slits. So now the argument is that photons go through single slits and interfere with themselves. Come on. Well, I don't want to be rude, but come on.
Exactly a half a wavelength farther than this one right here at the top, this very narrow portion of the beam, and this very narrow portion of the beam, if this travels a half wavelength farther than this one, then those two will cancel each other out. And now what happens is, if you look at the next beam right below that, and let me use a different color, so you look at the beam right below that, and then the beam right below that, again, those two beams will be exactly a half wavelength out of phase, and therefore when they reach that point over here, they will cancel each other out. And then if you look at the next...
Well, again, he's saying that point over there, these two obviously do have to converge to have that point over there. So, this is a little bit just not clear.
Portion of the beam right below that, and I'll use a different color again. And you take a look at this one right here. Whoop. I'll sink a little bit. There we go. Then you can see that those two blue rays also will cancel each other out because they will also be a half a wavelength out of phase. And in such a way, you'll see every small section of the beam up here will cancel out a small section of the beam over here. You can see that this first half of the beam will cancel the second half of the beam. So this beam cancels out this beam, and you'll see nothing over here. There'll be complete destructive interference. So therefore, you see a minimum.
Well, again, there can't be any canceling out. Like I said, the photon has to go somewhere, so it does go somewhere. So the beam can't get canceled out. It can only be the carrier wave that creates some sort of cancellation, and that the photon riding on the carrier wave, however that works, somehow, through some mechanism, does probability math that you're not explaining. So it somehow knows where to go. It knows where it can't go. How does it know where it's supposed to go?
So that's complete destructive interference. Now what happens when you have a greater lookup angle like this? Now you realize you don't have to go as far into the beam before you hit a point where this portion of the beam will travel half a wavelength farther than this one. So again, you have the same principle, that this beam right here and this portion of the beam right here, they're half a wavelength out of phase, so they will cancel each other out. And the ray right below it will cancel out this one, and the one below that will cancel out this one. But let's say, for example, that this is only 1/3 way into the beam. So you can see that the first 1/3 of the beam will cancel out the second 1/3 of the beam. So that this first portion of the beam will cancel out the second portion of the beam, and the third portion of the beam will actually still get through with nothing to interfere with. And so therefore you see a maximum. Of course, that maximum will not be as bright as the central maximum, because you realize here the central maximum is illuminated by the entire...
All right. So, I mean, this idea of all these multiple beams carrying, doing this canceling out with, just happens to cancel out with the one that's 1/3 out of phase. Why isn't it combining with the beam closest to it? Why is it waiting for a beam that's a distance that's 1/3 of the way away from it? So again, the diffraction, I mean, I don't think parallel lines is a really good way to describe, because it's a convergence. They have to converge at a point. And you can say that this convergence has a low probability, and this convergence has a high probability, and then you have to go back again to the angle that created them. So again, I'm still going to argue that this is angular dynamics, and it's not a, it's that there's no this is where it's decided where the photon will end up. Nothing happens in this empty space. Okay, here is where the photon is told where to go. It doesn't need to do any of this stuff. It can be told right there where to go.
Into the beam. Here, the first maximum away from the central maximum is only being illuminated by 1/3 of the beam. So this here is only 1/3 of the total beam, and that is then the portion that lights up that screen at that location. If you then look, understand really what causes that fraction in the first place. Well, illuminated by 1/3 of the beam. So this here is only 1/3 of the total beam, and that is then the portion that lights up that screen at that location. If you then look further...
Okay, so he's saying this is a secondary maximum, I guess, because the biggest maximum would be here. So again, he's arguing that the second maximum is 1/3 of the beam. Now, again, experimentally, I haven't seen this done. I haven't seen that sharp an interference pattern created by a single slit. And clearly, in the two-slit experiment, they're arguing that there is no harsh interference pattern, certainly not one this dramatic. So I don't understand that conflict.
Up again, you'll notice that maybe you only have to go into the beam 1/4 of the way before you find a point where it cancels out with this one, because there will be half wavelength out of phase. So the first quarter will cancel out the second quarter, the third quarter will cancel out the fourth quarter. So the whole beam will again be destructively interfered with, portion by portion, and then you'll see another minimum. Of course, that will be farther up the screen, and so forth. So the whole concept...
So again, another description where he's basically saying, look, the light got canceled out because the light beams were out of phase. And that doesn't happen. The light doesn't get canceled out. It goes somewhere else.
Of understanding diffraction patterns when you have a single slit is to realize that as you go further and further up the screen, if you have a greater and greater lookup angle, different portions of the beam will cancel each other out. And when that happens, either all of the beam will cancel out, you'll have a minimum, or a portion of the beam will make it through, and you actually will get a maximum.
Okay, so just for clarity too, so this math is the math he uses throughout these the series of things, and I don't really understand most of it, but I understand the geometry of it. Okay, so it's like a Feynman thing, it's the square of the, and then you do the time thing. But anyway, So what this is, it's just really about these angles that are created here in terms of the difference between this and, you know, this location. And to get to a single point here, there would be a distance here, and so that creates your triangle that you could do your geometry on to figure out what the phase difference would be. So that's the reverse of what he's saying, but I'm just saying this, the reverse of this drawing is that, you know, the point is where you know, where you can use any of these angles, but the easiest angle to use will be the biggest angle, which will be down here. Anyway, yeah, it's probably enough. Finish up.
So that's the concept of diffraction. Now we're going to take a look at one step at a time when you'll get a minimum, when you'll get a maximum, and how to actually calculate the distance of the screen, the angle associated with it, and eventually also the intensity associated with different portions of that diffraction pattern.
Right. So again, the math is going to be this math here, which is just going to account for the frequency of the light and the distance of the slit, which is going to basically define how much room there is in terms of a middle portion. I mean, you know, so it's the same math I would be using, in the sense that these are the important variables that are going to dictate how much diffraction there is. If the slit is very wide, there'll be very little diffraction because most of the light will be going through that wide part where it won't get diffracted. So, you know, that's sort of the argument. And that the wave function, the interference pattern, is being created by something not accounted for in his description, which is the vibration of the matter in these slit surfaces. Yeah, okay, so till next time. But anyway, enjoy the lectures, thanks. Appreciate that you make them. Hope you get more support, and generally speaking, yeah, I like them. I just don't. Again, it's an argument about the causes, not the effects, right? So I just don't think it's been proven or established sufficiently that the causes of these patterns are a function of photons, and that I think it can be reasonably argued that the causes of these patterns is a function of electrons affecting photons. Okay, I think that's the simplest way to say it. So, until next time. Thanks.